Good morning, good afternoon, and good evening, everyone. So today we're going to be doing some exercises in our scientific computing topics so far. And so I realized I had to do this because we haven't had much exercises here on each concept in our scientific computing course. So let's proceed to gradient descent. So what again was gradient descent? Gradient descent is basically an algorithm that helps us determine where exactly is the minimum or the maximum of a model or a graph or a curve or a surface, right? So here we were given an example, right? This is a real valued function ax squared over 2 minus bx. So that's a quadratic function. And if we were to find the gradient of that function, it's just this. And how are we able to do that? Well, we set we get the derivative of f, and then we set it to 0, and then we get x equals b over a. And then we can also do that with vectors and matrices in this case. So provided that we have ax equals b, where a is a matrix, x is a vector, and so we do a matrix vector multiplication, also known as a matvec, we get a resulting b vector. We want to find the minima of that function, right? But we just use this formula here, which is 1/2. We transpose our x vector, we multiply it by a times x vector minus b transpose x vector, given that our x has a set of x coordinates from x sub 1 all the way to n. And so here we have multiple variables to consider when we're finding the gradient. So here, as you may notice, we're actually taking the partial derivatives of our function f with respect to that variable, wherever it is, of x. And so this NB gradient, so from x sub 1 all the way to n, it actually shows instantaneous change of a function. And the vector is also direction of steepest descent. And so if we were to get the gradient of this thing, well, there, we're just taking its derivative. All right. But the thing is, I don't exactly know how this works underneath the hood. So here in this video, we're actually going to be doing some exercises. But that's the idea. We're trying to determine a minimum and a maximum of a given curve, a surface, and the like. Okay, let's do some examples actually. So here, this is solely based on my own. I'm going to be doing some examples. Let's try this. How about we find, so all of these exercises are all going to be finding the gradient descent of something, right? So here in this case, I want to find the gradient descent, let's say, of a simple quadratic function. How about that? And this quadratic function is given by a real valued function f. Say that. Let's say it's a perfect square. So we actually already know the minimum of this function, right? The minimum is at 3. Specifically, its minimum is at 3, 0. But let's use a gradient to see how we can do this. And so to compute for its gradient, we just need to get its derivative. So we do 2 times x minus 3, we do a chain rule. But that's just 1, so that's that. And then we basically set it to 0. And here we indeed see that x is 3 when we're solving for x, right? But let's make it more complicated. Or not necessarily complicated. Let's make it more into a gradient descent thing. So here's the formula actually for a gradient descent, right? Here's the formula. Or not really, yeah, formula. Actually, no, I'm not even gonna write it. So the idea is that so we want to make use of this iterative method, right? So this is x new, our new x. I'm gonna write it this way, is equal to our x minus, let's say, alpha times f prime of x, right? This x is basically our initial thing. So here's the idea. X old minus alpha f prime of x old. So our old x, the one that we're going to be plugging in, and then we're going to get something new. So let's follow that formula. So here's the idea. We're going to make some initial guess. We know it's 3, but we're going to make some initial guess. We're going to say x old or x naught is 0. By default, it's always going to be a 0 most of the time. And let's say that alpha, or we call it a learning rate, let's say 0.1. Another way we could have, anyway. And then what's the number of steps? 10, right? So how many steps? That's 10. Why is it 10? I'm going to show you in a bit. So maybe let's do some manual iterations. So here I'm not going to use code, right? I'm going to manually iterate this thing. So at step 0, well, that's x equals 0. When x is 0, we look at our derivative, and then we plug it in. And then we see here that that's my derivative, minus 6. So here we have an x. Now we use that new. So our x new is, what's our x? 0, right? What's our learning rate? 0.1. What's our function? 6. And then what do we get here? We get, oh shoot, this is negative 6. I just realized. So this is positive 0.6, right? That's the first one. Okay, let's take another step. Let's say x is 1. Or I'm kidding, x is 0.6. Because that's the x direction that we already got, right? X is 0.6. So we go to its derivative again. We get 2, 0.6 minus 3, right? And I believe this will give us times 2. Yeah, it actually gives me a negative value in this case, 4.8. And then we do our x new, 0 minus 0.1, the learning rate. And my new value would be 4.8 times 0.1, which gives me, oh, I forgot. So it's not 0 anymore. My old is not a 0. It's actually 0.6. Then my learning rate is still the same. And this would give me 1.08, right? So let's keep on focusing. Let's focus on that value, on those two values there. We see it's increasing, right? Let's keep going. Step 2. Here, this is x. Now it's currently at 1.08, right? So that's what we're doing. We look at its derivative, we get 2 times 1.08 minus 3. This is equal to negative 3.84. And so our new x value, which is 1.08, that's my old, my learning rate minus 0.1, and then my derivative negative 3.84. This is actually equal to 1.464. And so here's the thing. We can already see x is moving towards a minimum, right? And so here's what I'm going to do. I'm going to write some code to get this thing going. Okay. I'm going to write it in Python this time. I keep writing MATLAB lately. Okay. Let me go ahead and share this. Okay, hope it's visible. So the first thing I'm going to do is create that function, right? Yeah, I'm going to create that function. Create function. I'm going to define that function, and it has some input x, and then, yeah, so here I'm just going to return that quadratic, right? And I think this was to the 2. Okay. And then the next thing I'm going to do is I'm going to also define its derivative. And so how do we do that? So we just do df, I guess. So here I'm going to define its derivative. We're also gonna input some x. And then this is gonna return me x minus 3, right? That's the derivative, 2 times x minus 3. And then from there, the next thing I'm gonna do, let me see if it runs first, actually. I'm running Python 3. Okay, it runs. Next thing I'm gonna do is start with an initial guess, right? I'm gonna say x is equal to 0. My alpha is equal to 0.1, because that's my learning rate. My steps, we do 10. So my steps and my x is something that I just guess, right? I don't know what these are. I'm gonna say x and steps are totally my guess. Okay. So I have these initial conditions, right? And so the next thing we want to do is we now want to do that iterative process. So for I range, in that range, I'm going to include steps. And then in here, I'm going to say, okay, we want to find gradient. This is df. How do I code this up? df of x, right? So we plug in our x. Goodness, now I can't see. Okay, we plug in our df of x. And we're getting the gradient, right? Yeah, because we're getting, so we take the derivative and then we're getting our new, oh no, we're just assigning it to that. So actually the derivative here is also the gradient. That's the thing. And we're gonna see another example in two variables. Okay, so we get that gradient, we get a new x value, right? So this is x is equal to x minus its alpha times that gradient. Or actually what we could have done, let's just do this df of x. Okay. And then from there, now we can print at each step, right? So I'm going to say, while we're doing this, I want to print this at each step. So step, we're going to put that step there. And then we're probably going to put the x value as well as the f of x, right? So the x value is going to be, well, x, that current x value. Let's say up to 5. And then our x value. Here we say, what is this? Well, I guess we evaluate it at that function, right? So it's f of x. Then here we do this. Just to say we want it in 5 decimal places. And then we're pretty much done. So this is the iterative process, getting to that minimum. And now I think that should be good. So let me quickly run that. And here we see, oh, so we start from 6. We keep going. And by step 9, we get to 2.6. So we're actually getting extremely close to 3. Right? We're getting extremely close to 3. And we can actually plot this. Or, okay, let me try something. What if we make our steps 13? Now we're getting even closer. If we make it 17. Oh, we're getting even closer. 2.9. Okay, now you might be asking, what if I make it 1,000 or 100? Okay, now it's exactly at 3. Right, so either way, we're gonna get to exactly 3 when our function, or when our function is 0. Oh, our function will be 0 because 3 minus 3 is 0. So either way, we're gonna get exactly a 3. And so it's just this idea of choosing the right alpha in order to get to there. Well, this is a basic function. It's a quadratic. If we were to do something different, like let's say a very complicated function that doesn't converge to anything, that's another thing. Then that's where gradient descent really becomes super useful. So here it's just a numerical method for helping us identify the root. I'm kidding, not the root, the minimum or the maximum of a given function, whether that's one variable, two variables, three variables, etc. And here we see that it definitely has a minimum at 3. We could have done it algebraically. I'm just showing a way we could do it using this gradient descent. And we could even plot a descent path. So we could, let me just do that real quick. Then I could even try different learning rates. So here, I'm pretty sure it converged at step 59. So it took 59 steps to do that. If I put my learning rate to be 0.5, say, well, now it can, oh, at step 0, it's at 3. So it would go there automatically, right? So here it's also about picking, and similarly, let's say 0.1 here. Let's say my x starts at, let's say 7. How would that fare? This were to start at 7. Well, here now it's going down because that's what the algorithm is. It's going down until it reaches a minimum, 3.4. If we keep on going, say 100, we get all the way to 3. But at what step? I'm guessing 58 again. 3.1, 60, right? Here that's 3.00001. And then here 3.00. Yeah. So this is where it kind of converges already at step 60. So whatever x value we start with, we're always going to get to that minimum or maximum depending on the function. We could do it algebraically again, but this is another way of doing it. And here we can see this helps us identify that, oh, it converges at this step. But again, we have to choose the right steps, and we also have to choose an x and as well as our alpha. So these three things are something that we have to choose, right? Okay, let me go back to wait, open chat. Let me go back to my here. Yeah, so here we did initial steps from all the way to 2, and then we just keep on going until we go to 3. In this case, it's 58 steps if we were to do it. So that's extremely slow. But anyway, oh yeah, let me also show the plot for this because this seems interesting. I'm going to show the plot real quick. Where is my sharing? Oops. Let me quickly show the plot here. So here, as you guys can see, so that's our function x minus 3 squared. And there we have it. See, as we're going down, these red dots, I don't know why I said yellow. These red dots are the number of steps. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Apparently there's an 11 there. Not sure why. But those are the number of steps we took. And this is supposed to be 10 steps. Oh, so our initial point here was 0. We keep going. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we took 10 steps to get to that point. And this would be different if we had different values. Let's say if this were to start somewhere at, say, 5, I don't know. If we were to start at 5, now we would start at the other side. And here we would take 10 steps again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are 10 steps starting from 5. But as we go, we're going to converge to a solution. And then, I don't know, if we make this 100, well, that definitely should converge to something. Or it should give me a solution. And there we have it. So those are 100 steps. Each red dot is one step. Those are 100 steps. Okay, let me go back. Now let's move to a different example. Let's do this time something with variables. Okay, but there is a visual and a clear convergence towards the minimum at x equals 3. Okay, now let's move on to a 2D function. So here, as we're talking about in my calculus course, we've recently gone to talk about functions of two variables, functions of several variables. And now we're going to apply that here. Okay. So here, what do we see? We have a gradient descent. Oh, jeez. I'm not writing anything. So here it's a gradient descent. On a 2D function. So here it's not quadratic, it's 2D. So how do we do this? Well, first we need the function, obviously. So here we have x squared plus y squared. And so actually the minimum here is where? The origin, right? Okay. So how do I go about finding the minimum or maximum of this function? Well, again, we take the derivative. In this case, it's a function of two variables. So I take its partial derivative, and that would give me my gradient, right? So now I am confident I can write this notation. That upper triangle thing, that means gradient of the function f. And so the gradient of that function f is a vector of some sort where we take its partials, right? It's partial with respect to x, and then it's partial with respect to y. And if we take those, we will get 2x for one, 2y for the other, right? Because that's what we're doing. For if we look at here, we have an x going all the way to n. Here we have x sub 1 going all the way to n. That's basically what we're doing, right? Now you might ask, why am I doing it as a row vector instead of a column vector? Mm, it works, any works. I'm just solving it. I'm gonna make it a column vector anyway. So here's how our gradient descent update rule is gonna be. So remember how we did x new, x old minus the learning rate alpha, and then its derivative? So here's how we're gonna update it. We have our new xy value. That's our x new. Our x old value is going to be this xy. This is minus alpha, that learning rate, and I multiply that by my derivative, or in this case, my partial derivatives. So that's how we're gonna do it. Okay. And don't worry, am I gonna manually solve it? I don't know. We'll see. And so we can actually simplify this, right? Now we have two things that we're doing. Our x nu is equal to x minus 2 alpha x. And then our y nu, our new y value is y minus 2 alpha y. All right, so we have two things that we're considering. Like the first one you only need one. Here we have two, because we're finding the minimum of two slopes, right? Because you have two derivatives that we're trying to take care of. Okay, so thankfully I'm not gonna do this using or by hand. I'm gonna do this with code. So let me go ahead and do that. Here's my sharing. So here's how I'm gonna do that in code. I'm also gonna do the plotting. Might as well do it. So here's how we do it. So first I'm gonna import my libraries. NumPy for easier linear algebra stuff. Matplotlib for plotting. And then I'm going to find the function as well as its gradient. That's what I'm going to do. So I'm going to define function. And here in this case, we call it a gradient, not a derivative. So my function is again x squared plus y squared, right? Now you might be asking, where in the world is my y? Because I have it one variable and two. And what's my gradient? Well, again, that's just going to be, let's say, the gradient of the function. So grad f, we have two variables x, y. Here we're going to say, and I think I returned it as an array, yeah. So I'm supposed to return it as an array. I'm going to use my numpy array. And here I return both of them. So 2 times x, 2 times y. Right? Those are the things that we got from taking partial derivatives. And then from there, now I initialize my parameters. So what do I mean by parameters? I mean my initial guess, my x naught, my alpha learning rate, my learning rate alpha, as well as the number of steps I want to take. So here we initialize my parameters. So here my x is initially going to be, it's really just some random guess. Anything works. Oh, my x and y rather. So my x and y. Let's say one's 4, one's 3. How about that? What else can we say? Maybe my alpha is, let's keep it simple. Let's keep it 0.1. And let's say my steps, let's make it 20. I don't know if there's gonna converge exactly, but it should, right? And then we're going to do the gradient descent thing. And we're also gonna make a contour plot. So again, was a contour plot in our calculus? So in calculus, a contour plot is a way to identify how a curve, or in this case, how a surface looks like based on level curves. So that's what we're gonna be doing in code. I'm not gonna write it out. So here's what we're gonna do. We're gonna perform the gradient descent algorithm. We're gonna we're literally gonna do it. And it's the same iterative process as the thing that we've been doing. So I'm gonna say for blank in range. We're gonna loop 20 times. We're gonna do this 20 times. Let me do this. Okay. This is just distracting. And then here, I'm gonna get the gradient, which is grad f of fxy. Yeah, I'm just gonna simplify like that. Doesn't matter. I'm gonna say, yes, my x is, or I'm gonna shortcut this, x minus equals, which just means x equals x minus. It's the same thing as this. X equals x minus dot dot dot. Right? It's the same thing as that. So x minus equals the gradient times. And then we multiply it to my. Oh, wait a minute. I just realized. Hmm. Oh yeah, my alpha, right? Times my gradient. Here, at index 0. Right? Then we keep going. My y and my alpha times the gradient at 1. These are just indices, as you might be asking, because this is coding. So when we look at the gradient at 0, we're basically looking for this. We treat this as an array, and this is index 0. And if we're looking at index 1, then we're looking at this. That's the data structure in computer science. We have an array. We treat everything as an array. And these are at each position of that array. We call them index or indices. And the first index is always going to be 0. That's why we get 0 here, because we want to multiply it by that derivative. Then here for y, we get 1, because that's what we want to multiply it with 2y. And so from there, we keep going. So here, okay, here's what I'm going to do. I'm going to append it exactly, the path. Okay. Let me see. Oh, so I want to store my path first before I. Yeah, yeah. Let me store my path. This is where I just store all of my points. So here I can keep track of what the path is, right? X. Because I want to keep on doing it again and again. And yeah, I want to store it. Because I'm also planning to graph it. Okay. And then you want to convert it to arrays for plotting. So that's just me for plotting purposes. So this is path. We're gonna convert it into an array. Okay. And then from there, what do we want to do? We want to make a contour plot, right? Contour plot. So this is going to be some y that we're going to initialize. So x, y, mesh grid. So mesh grid is a built-in function from NP or NumPy. And what exactly is mesh grid going to do? Well, we can Google it. NumPy. So there's a built-in function in the NumPy library in Python. It generates an n-dimensional coordinate arrays. Right, so it gives me x, y, z arrays, n by n dimension arrays. That's what's gonna do. Okay, I'm just gonna code this up. So here, I'm gonna do a line space so that we get equal spacing. And this is going to be from, I don't know, this is really random, to 100, and as well as the other one. So here we just copy and paste this. Cool. Okay. And then now we have our output, which is again our function at x and y. Right? So let's just make making a contour plot, basically. Then we have a plot. Okay, I'm just gonna copy paste these. These are okay. I thought I could code them all up, but I guess yeah, I can't do it all on my own. Oops. Matplotlib. Oops. Did I? Oh, pyplot. There we go. Okay. Yeah, I was seeing some errors. Okay, now I'm gonna run this. And here, I hope this shows it. It's taking a while. Or did I? Oh, there you are. Okay, so here's the gradient descent for that. Here we have a contour plot. Yes. So here we can see that the minimum is exactly here at this stop, right? It looks like I'm getting hypnotized. So basically, again, it's gonna take steps again and again until we reach this particular minimum at 0, 0. Now, if you might be curious, because I am also a bit curious, what exactly is x squared plus y squared? It's a sphere, right? Let me do this real quick. I'm gonna go to Desmos. I'm gonna graph it out because it's easy to do it. Okay, where's my thing? 3D calculator. There we go. I'm gonna graph it out. So we have z equals x squared. I don't think I actually don't think it's a. Oh, it's an elliptic paraboloid. Yeah. And so if we look exactly at my xy, what in the world? That's my positive. There. That's what it's showing me at each level of Z. There. My minimum is exactly here at the bottom. So if we were to just do this, my minimum is at 0, 0, 0. And there you have it. There's my minimum at the very bottom there of that elliptic paraboloid, right? And so it's the same thing here. But here we're taking a series of steps to get to that minimum and we're using a contour plot to visualize how it works. Okay. And yeah, we're taking 20 steps. So these are 20. Okay, That's that's it. That's it for this video. I don't know why I said that so many times. That's it for this video. I hope you guys enjoyed. I hope you find this really interesting. And yeah, I'll see you guys in the next one.